In networking, messages are often larger than what the network can carry at once. When that happens, messages do not fail immediately. They are fragmented. Message fragmentation is the process of breaking a single logical message into smaller pieces so it can move across the network. Those pieces travel independently, and later they are reassembled into the original message. Fragmentation exists because networks have limits. Links have maximum transmission sizes. Buffers have finite capacity. Not everything can be sent in one piece. Fragmentation is how networks adapt without forcing applications to change how they think. So what is message fragmentation? Message fragmentation is the division of a complete message into smaller fragments for transmission, with the expectation that those fragments will later be reassembled to reconstruct the original message. The key idea is that fragmentation changes how a message is transported, not what the message is. From the application's perspective, the message remains whole. From the network's perspective, it becomes many parts. This separation allows communication to continue even when message size and network constraints do not align. A helpful way to think about fragmentation is moving furniture through a doorway. You do not change the furniture, you break it into pieces, move them through the door, and reassemble them on the other side. Now let's look at how message fragmentation works. Fragmentation typically occurs when a message exceeds the size a network path can handle in a single transmission unit. The message is divided into fragments, each small enough to pass through the network. Each fragment carries enough information to allow correct reassembly. This includes identifiers that tie fragments to the same message and indicators that describe fragment order or position. Fragments are transmitted independently. They may take different paths. They may arrive out of order. Some may arrive late. Some may not arrive at all. At the receiving end, fragments are collected and reassembled into the original message. Only when all required fragments arrive can the message be considered complete and delivered upward. If fragments are missing or corrupted, reassembly may fail, and recovery mechanisms must decide what to do next. This leads directly to why message fragmentation matters. Fragmentation enables flexibility. It allows applications to send messages without knowing the constraints of every network path in advance. But fragmentation also introduces risk. Each fragment is a point of potential failure. If one fragment is lost, the entire message may be unusable. Larger messages which require more fragments are therefore more fragile. Fragmentation also increases overhead. Each fragment carries its own headers and metadata. This increases total transmitted data and processing cost. Fragmentation affects latency. A message cannot be processed until all fragments arrive. One delayed fragment can hold everything back. Because of this, many systems try to avoid fragmentation whenever possible. They prefer to size messages, so fragmentation is unnecessary. Now let's examine the defining characteristics of message fragmentation. First, fragmentation is a transport concern, not an application concern. Applications deal in messages. The network deals in fragments. Second, fragmentation creates dependency between fragments. Fragments are meaningless in isolation. They only make sense when combined correctly. Third, fragmentation increases sensitivity to loss and reordering. More fragments mean more opportunities for failure and delay. Fourth, fragmentation requires reassembly state. Receivers must track partial messages, manage buffers, and handle timeouts for incomplete reassembly. Fifth, fragmentation introduces cleanup complexity. Fragments that never complete must eventually be discarded to avoid resource leaks. These characteristics have significant implications for network behavior. Fragmentation amplifies the effects of congestion. When networks are overloaded, fragments are more likely to be dropped, delaying or preventing message completion. Fragmentation interacts strongly with message boundaries. Even if fragments arrive, incorrect boundary handling can prevent correct reassembly. Fragmentation also affects security. Fragmented messages can be used to evade inspection or exhaust resources. Many security controls must account for reassembly before analysis. In distributed systems, fragmentation can influence system design decisions. Large messages increase fragility under failure. Smaller messages reduce fragmentation but increase coordination overhead. This is why many protocols and applications enforce size limits, batching strategies, or chunked transfer mechanisms. They are all responses to fragmentation trade-offs. Message fragmentation is not inherently bad. It is a tool. Used carefully, it enables flexibility and interoperability. Used carelessly, it introduces latency, overhead, and instability. Messages express intent. Size defines cost. Fragmentation manages constraint. When you understand fragmentation, you understand why networks prefer smaller messages, why large transfers are handled cautiously, and why reliability mechanisms exist. Fragmentation is how networks cope with reality. That is message fragmentation.